Laboratory 7 Instrumentation Amplifier with PPG and ECG demo. In this lab, we're going to start by building on your breadboard this classic instrumentation amplifier circuit consisting of 2 op-amps at the input and then a third op-amp that is a standard subtracting or differencing circuit at the output. Here's the actual circuit that I built. Notice that I wired it onto the breadboard very carefully, and I cut the leads of the resistors to avoid short circuit possibilities. So I would ask that you do likewise. Obviously you don't want to cut the leads of the resistor too short that they won't plug into the breadboard, because you will be using those resistors in other circuits later. But at any rate, notice that this first TL072 package, it holds the 2 input op-amp buffer amplifiers, and then the third package, we're only using one of the op-amps that is in it for the output stage. Just sort of looking at how I wired the circuit up, I did try to keep the resistors, these 3 vertical resistors, fairly vertical. They can't be perfectly vertical or they'll be shorted out. Of course, that one is the middle one, R1. That one is R1 in the middle, and then the 2 top ones are the R2s. And then notice that coming over here, I have a vertical resistor going between pins 1 and 2. That is the feedback resistor right here. And the 2 input resistors are here and here, both horizontal, trying to make, here and here are the 2 input resistors. And then this resistor, which is vertical in the schematic, I also made fairly vertical right here on the breadboard. I brought the V- and the V+ inputs over in the same relative position. This is the V-. No, I'm sorry. The top is the V+. That kind of makes more sense anyway. And the bottom is the V-. That's how I brought the wires out. So over here is a little voltage divider that is in figure 2 of your lab handout. There it is. And I want you to start by connecting this to 3 volts, as you can see, 3 volts. And then we're making a little voltage divider up. This voltage divider is to allow us to get a very, very small but very accurate DC voltage for testing the instrumentation amplifier, the circuit that we have wired up. And so here, notice that at the output of the voltage divider, I'm connecting that very small positive DC voltage to the V+ input of this instrumentation amplifier, and I am grounding the V- input with this wire right here. Now, the overall gain of the instrumentation amplifier is calculated here to be 700. And so taking that very small voltage that is divided between the 10 ohm and the 3000 ohm resistor and multiplying it times the AVD of 700 gives us an expected output voltage of 6.976 volts. So let's actually see what voltage that we measure on the DC voltmeter. And as you can see, it's not quite the expected 6.976. It's a little higher than that, as you can see. Furthermore, putting that aside for a moment, what if we reverse the two inputs? I'm going to feed that small positive voltage that is coming out of the voltage divider into the V minus input now, and I'm going to ground the V plus input of our instrumentation amplifier the way I've connected it now. Well, now we would expect to, of course, see negative 6.976 volts. However, we end up reading negative 6.39. We're off a little bit. It's a little bit off from the 6.976. But here's the thing. Cheap op amps like the ones we're using often have a small DC offset. And that DC offset can be calculated by taking the average value of the two measurements that we just made, here and here, adding them together and dividing by 2, we get 0.631 volts. That must be the DC offset that is messing up our measurements slightly. So let's take the first measured voltage when we fed our divided voltage into the V plus and grounded the V minus, we got 7.656 volts. If we subtract off our little DC offset that we calculated here, we get 7.024 volts. That's our corrected output value, so to speak. Likewise, if we take the second measurement that we got when we reversed the V minus and V plus inputs, we got, if you recall, negative 6.393. Well, if we subtract the offset voltage calculated here from that, we get negative 7.024 volts. So apparently what we measured is off by the DC offset of 0.631 volts. And when we subtract off that DC offset, we have exactly what we would have liked to have seen, or very, very close, I should say, to what we would like to have seen. We would like to have seen this, recall, and we now get this, which is extremely close, within just a % or so. Now I have tied both the V plus and the V minus inputs to the same 3 volt point that's coming in from the 3 volt power supply. And of course, an ideal instrumentation amplifier, when you tie both V plus and V minus inputs to the same voltage, no matter what it is, in this case it's 3 volts, should give us 0 volts out. But look what we're getting on our DC voltmeter. We're getting something very close to that DC offset that we calculated. Recall, we calculated it to be 0.631, and we're reading 0.600. So apparently this instrumentation amplifier is working fine, except it exhibits this pesky little 0.63 volt DC offset. The way we can get away from this problem is to go to AC. So we're going to ignore the DC offset and just concentrate on AC signal amplification, which is usually what we're interested in anyway. So we're going back to our voltage divider, and instead of using a 3 volt DC source, we're going to use a function generator hooked up to give us a 3 volt peak to peak 1 kilohertz AC waveform. So now I've gone to AC excitation of the voltage divider, and actually the lab calls for us to set up a 2 volt peak to peak or a 1 volt peak 1 kilohertz sine wave being divided by that same resistor ratio, that same voltage divider circuit, 3K and 10 ohms. So here's the scope screen, and notice below the peak to peak on the input is 2 volts, very, very close to 2 volts. And the peak to peak measurement on the output is 4.69 volts. So here are the calculations to see what the observed AC voltage gain is. we take the output peak-to-peak voltage, 4.69 volts peak-to-peak, and divide it by the 2 volt peak-to-peak input voltage times the division ratio, that very severe division ratio of 10 over 10 plus 3000. Anyway, the gain comes out to be 705.8 when the predicted gain was 700. So as you can see, our percentage error is well less than 1%. So it's much easier to measure the gain of this circuit at AC, because at DC there is that pervasive 0.6 volt DC offset. We don't have that problem now. So I could swap the 2 inputs around. Let me do that. And so now it'll be the V minus that is connected to the output of the divider, and the V plus input is now connected to ground. And now the output stays exactly where it was. Of course, it's turned upside down, but the output, the peak-to-peak output there, that's the bottom waveform, by the way, is still right at 4.69 or 4.68 volts. So that's what we expect, of course. Now the next thing to try is to check the common mode gain, which we hope is very low. And we really could not measure it accurately at DC because of the DC offset. It would have been a pain to try to measure it, but it's quite easy to measure at AC. So I'm simply going to tie the 2 inputs together. The V plus input is here, and I'm going to connect it to the generator, directly to the generator without going through the voltage divider. And I'm going to connect the other input of the instrumentation amplifier to that same point, right across the generator. Then we're going to readjust the generator for a higher voltage, and hopefully the output will be very, very low. So I'll be right back with that. So now that I have the function generator connected to both of the inputs of the instrumentation amplifier, both the plus and the minus inputs, of course ideally the output will be 0. On the scope here I've got the input set up for 20 volts peak to peak, a very, very large value, and the output is less than, is just about half a volt peak to peak, as you can see from the quick measure display. So taking the ratio of the half a volt coming out to the 20 volts peak to peak going in, we end up with a common mode gain that is very close to 0, 0.0255. And of course, we would desire it to be exactly 0. So it could be better, but the CMRR comes out to be the differential gain, which we measured to be 705, divided by the common mode gain that we measured, 0.0255. So we come out with a whopping 27,647 for our CMRR. Now, of course, it could be better, it could be higher. A commercial instrumentation amplifier might have a CMRR spec of 1 million. Of course, we could make our CMRR higher if we took efforts to match the various paired resistors, the RFs, the RIs, and the R2s in the circuit that we showed back here. So now that we've measured our CMRR and found this to be a pretty good differential amplifier, now we're going to have some fun with it. And the first thing, we're going to use it as a single-ended amplifier to amplify the signal that is received from a infrared emitter circuit. This is an infrared light emitting diode. It has the longer I'm sorry, the shorter leads. This is the infrared light emitting diode over here. And we're going to hook it up in the circuit that is shown in figure 4. Or figure 5, I guess. And we're going to use the reflective mode, where the infrared LED launches infrared light into the finger, and it bounces off the bone, and it comes back and is received by the phototransistor. And the one with the longer leads is the phototransistor. Notice I've marked that clearly in the schematic diagram. So we're going to wire up the infrared LED to launch infrared into the finger, and then we're going to wire the phototransistor, which acts like a light-controlled current pump that pumps more current when more light enters it, through that resistor, R9, the 1.2K resistor, and thereby generates a time-varying voltage which is passed through the capacitor. A capacitor will pass time-varying voltage, but we will not pass constant voltage. So we only are interested in the time-varying component of the light, because that's the light that follows the pulse. When the blood is pulsed through our finger, it's going to attenuate or cut down the light beam a little bit. So there will be a DC component to this output signal that we are not going to pass through the capacitor. Capacitors will not pass DC, they'll only pass AC. So that's the purpose of this capacitor and that resistor R10, is to form what we call a high-pass filter, which will only pass the pulsation portion of the light signal, which is what's going to be displayed on the scope, so we can basically take our pulse. And this application is called a photoplethysmograph, or a PPG. So here's the setup. The output of the photo detecting circuit, the phototransistor, and that little 1.2K resistor going to ground. I'm taking the output there, but at the junction of the phototransistor and the 1.2K resistor, and I'm running it over to the V plus input. I'm grounding the V minus input. And so we're amplifying the voltage. That changes just the component that pulsates, because we're passing it through the 1 microfarad capacitor and the little 1 megohm resistor that forms a high-pass filter. So we're only passing the pulsating component that is received at the photodetector. And of course this is the LED that is sending out the infrared. So I need to put my finger right across these two guys so that the light beam bounces off of my bone, and I've got to keep my finger very, very steady, and if I do that, I get a PPG signal, and the period of this PPG signal is giving me my pulse rate. 1 over that period gives me the pulse rate, and well, I have to also make it pulses per minute, I guess. It's in pulses per second. But there's my PPG waveform, and you'll see that the period between two peaks is approximately 1 second, because we're on a ½ a second per division scale. Now there is a certain amount of noise in that PPG because of the 60 Hertz pulsating light that is coming down in the room and hitting my finger. That's causing noise pollution in the PPG, and I can prove that if I turn the lights off and look at the PPG then. So take a look at that fuzziness of the line in the PPG, and now I'm going to turn the light off and it's going to look a lot better. Be right back. So now I've turned the light off, and I put my finger back in position, and it takes a little while for the circuit for the op amp to come out of saturation. There we go. Do you see now the PPG is less fuzzy? It's much more distinct now. And what we're basically doing is measuring the blood pressure in our finger versus time, and we see how it peaks as the ventricles contract and squeeze blood into the arteries. Now we're going to the ECG demo, and as you can see, we've added another high-pass filter. So we have two identical high-pass filters, one at the V plus input and one at the V minus input, and these are going to be connected to horizontal chest electrodes, and we'll also be grounding the right leg to drain off much, but not all, of the 60 Hz common mode noise that is picked up due to proximity to the power line. And we're going to amplify the heart signal differentially, while the 60 Hz garbage, common mode garbage, is going to be largely subtracted out. Although not perfectly, because as you know, our CMRR is not infinity. Our common mode rejection ratio was big, but it wasn't infinite. So that means we will be getting some 60 Hz noise on our ECG recording. So these are the electrodes that we're using to record the ECG, the electrocardiogram, and they consist of conductive jelly and adhesive so that they can self-stick to the body. And underneath the conductive jelly, which is salt impregnated glycerin, it's called electrode jelly, is a graphite block. And the graphite block has a hole drilled in it where we can plug in there it goes, where we can plug in a wire. So that's how we make contact to the electrode, and these electrodes are used for pain reduction units called TENS, TENS units, and they turn out to make very nice electrodes for picking up heart waveforms as well. So now I'm going to attach the electrode to my chest, across my chest, so it's across the heart, and I'm putting one down here, and it'll stick. If I press hard, they're kind of been used many times. They're really only supposed to be used once. And I can put another electrode across my chest, like that. So now I have them across my heart. And then I can put another electrode down low. That's the grounding electrode. And I can even put it down on my leg. On my right leg. That's typically where it's put, and that reduces the common mode 60 Hz noise that's picked up by my body because of proximity to the power lines.
Stopped.
So here is a normal EKG. I have my wife hooked up to the electrodes that are placed horizontally across her chest, and a grounding electrode on her right leg. And notice that we have the P wave that indicates the contraction of the atria, squeezing the blood into the ventricles, and then this is where the ventricles are firing, the QRS complex. And then there's the recovery wave, the T wave, where the ventricles relax and get ready to squeeze out the blood into the arteries. The ventricles are 90% of the heart, which is all one big muscle, because it takes a lot of pressure to squeeze the blood into the arteries, which are already at a high blood pressure. Notice the peak in the ECG waveform, which is the QRS complex when the ventricles contract, is delayed a little bit from the peak in the PPG. That indicates the maximum blood vascularity, or the light beam is being blocked the most when the PPG peaks. So that represents a pulse of blood going between the phototransistor and the LED. Anyway, notice that when the ventricles contract and when that pulse of blood, when the PPG maximizes, there's a delay of just a few tenths of a second. And that, of course, represents the travel time of the pulse wave. Now, when I talk, I kind of wiggle the PPG, so I've got to not talk for the PPG waveform to be clear. Notice the period of the PPG and the period of the ECG are the same, roughly 1.5 divisions. About 1.5 divisions. And we're on half a second per division, 500 milliseconds per division. So my pulse rate is 1 over that time period. As you can see, if I don't talk, the PPG is much clearer. So now I'm going to just look at the ECG waveform, and I've increased the amplitude so it fills more of the screen. And you can see that it's not a perfect ECG. There is 60 Hz noise. You can see that fine structure wiggles. That's covering up some of the details of the ECG. Nonetheless, if I take off the grounding electrode, which is keeping the common mode 60 Hz noise low on my body, there's going to be quite a bit more 60 Hz noise. In fact, so much that it will really cover up the details of the ECG. So let me unplug the grounding electrode that's connected to my right leg, and we'll see what happens. Here goes. Okay. Now you can see that the 60 Hz noise that's appearing is far more objectionable, and it really covers up the preliminary contraction of the atria. I'm going to put the ground back on now, so that now the common mode noise on the body is greatly reduced. There it is. Now we're back to where we were. Only now can we even see the atria contracting, which is just before the QRS complex. There's that very small pulse, and that was completely buried in the 60 Hz noise. There it is. P wave. The P wave is very hard to see on this ECG waveform. Here is the ECG when the electrodes are placed differently across my chest. Instead of horizontally, I have them placed vertically. And now a rather different heartbeat waveform is seen. That's because we're actually looking at a projection of the cardiac vector as the heart beats. The cardiac vector changes position, and we're projecting it on a different baseline now. It's like we're drawing a line between the two vertical electrodes and projecting the heartbeat electrical dipole along a different pair of lines, and so it's quite a different shape. Okay, this is a demonstration of the electrooculogram, the EOG. I have the electrodes on the left and the right side of my temples, just near my ears, and I'm going to pick up my eye movements. And so I'm going to move my eyes back and forth, and I'll be able to pick up a signal that indicates that I've cocked my eyes from left to right or right to left. So looking to the left, looking to the right, looking to the left, looking to the right, looking to the left, looking to the right, and now I'm looking straight ahead. You could actually gauge how fast I'm reading a line of type. Left, right, left, right, left, right. And now straight ahead. Now I can also look straight ahead, and then while I'm focusing on something straight ahead of me, I can move my head back and forth, and I can get the same effect because my eyeballs will track that point that I'm locked on to as I move my head back and forth. So looking straight ahead at a point and staying on that point with my eyes, I'm going to turn my head to the left and to the right. Left, right, left, right, left, right, left, right, left, right, left, right, left, right. So you can get the same effect. That's called the EOG. Now I've placed the electrodes across my lower arm to try to pick up signals from the lower arm muscle. Right now my arm is completely relaxed as best I can, and the scope is showing pretty much just a flat line. But when I start to make a little bit of a muscle, like this, just a little bit of muscular effort, you'll see that the scope begins to register muscular activity. And as I tighten it up more and more, now I've really got a lot of muscular activity. You can see the random spikes that are occurring. Now I've relaxed it again. Too bad the scope doesn't trigger constantly. And now I'm going to, in mid-sweep, okay, I made a muscle and then I relaxed it all within mid-sweep. I'm going to turn down the sweep rate of the scope so we have a little more time. Okay, make a muscle, make a really strong muscle, then make a middle effort, and then no effort. So you can see what that looks like. I'll try it again. Little effort, a lot of effort, and then back to no effort. So what this EMG situation can do, when you put electrodes across a certain muscle, is monitor the muscle activity, the muscular exertion that a patient perhaps is making over an amount of time. And you could feed that waveform into a integrator, which would add up the area under the curve, that muscle activation curve. Now I'm really making a muscle, as you can see. I'm really making an effort, and I'm really making that EMG explode there. So that's the idea of an EMG. So we've looked at an ECG, electrocardiogram. We've looked at an EOG, an electrooculogram. There I go, making a muscle again. Relax, muscle, relax, muscle. And we've looked at this EMG, electromyogram. That's the muscle waveform that we're looking at on the screen right now. And again, make a muscle, relax. Make a muscle, relax.